Hello everyone, welcome back to IB Math Applications and Interpretations. Today is topic 3, lesson 2. We're talking about the Triangle Sum Theorem and Intro to Trigonometry. Our EQ is what skills are required to solve a triangle. 12 triangles, everyone loves them. The great thing about today is that you've already learned most of it, so think of it like a review kind of lesson. So instead of Intro to Trigonometry, we should really call this Review of Trigonometry. So you're not learning anything new that you haven't already done before. But a major skill that you need to have in geometry is to solve a triangle, which means you need to find all its missing side and angle measures. Now, you already know how to find a missing side of a right triangle by using the Pythagorean Theorem. And we'll get back to sides of triangles in a minute, but let's take a detour and talk about angles of triangles. So here we can see that we've got a couple of parallel lines and some transversals as well, and those transversals cutting through end up making a triangle. And quick apologies ahead of time to Mr. Boucher because I'm probably going to butcher all the geometry vocabulary and language here, so bear with me and we'll let him yell at me if I get some things wrong. But we're looking at this at these parallel lines and seeing that these transversals create a triangle, and that's going to be really important to us because we know that intersecting lines through parallels can find all sorts of interesting angle relationships. And this is something you did back in geometry, but let's prove it's true in what's known as the Triangle Sum Theorem. The first thing that I want to recognize is that I've got a few angles here that have made a straight line. So I'll call this angle 1, we'll call this one angle 2, and we'll call this one angle 3. Now, angles 1, 2, and 3, since they make a straight line, will sum up to 180 degrees. So I'm just going to jot that down over here. That angles 1, 2, and 3 add up to 180 degrees. And that's important because I noticed that there are some relationships. Like I'm going to call the angles in this triangle angles 4, 5, and 6, respectively. And I notice that angles 2 and 4, these make an interesting pair. These we call vertical angles, and we know that they are congruent to each other. So angle 2 is indeed congruent to angle 4. Also, I see that these ones, I believe these are called corresponding angles. Angle 1 and angle 6, these make a corresponding angle pair, and corresponding angles through parallel lines like that are indeed also congruent to each other. We can also find the same is true for angle 3 and 5. Angle 3 and 5 are also corresponding pairs that happen to be congruent to each other. So why this is important is because now we can say that, well, if angle 1, 2, and 3 sum up to 180 degrees, so will angles 4, 5, and 6. And that's important because this was just any random triangle, and this will hold for any triangle as well. And this is what's known as the Triangle Sum Theorem. The Triangle Sum Theorem says that the sum of all the interior angles of any triangle will always add up to 180 degrees. Why is that important? Because that's going to allow us to solve some really arbitrary super nerdy geometry and algebra style questions like the one that we see here. So we want to determine the value of x in the triangle at the right, and we see that we're given all these angles, but we're given them in terms of weird algebraic expressions. But it's not a problem because we know the Triangle Sum Theorem. We know that the sum of all three of these algebraic expressions will add up to 180. So we can set up that expression, adding up the angle 7x plus 8, 5x plus 2, and 7x minus 1, all of those adding up to 180 degrees. Next, we'll combine all our like terms, just to do some simple reorienting of this expression. Now, we'll do some simple algebra by subtracting the 9 from both sides, and then dividing both sides by 19 is going to give us 9. And we have very easily, using the Triangle Sum Theorem, solved for this really seemingly obtuse and arbitrary triangle question. But one of the things we like to do more often is look at right triangles. Right triangles exist all over the place in the real world as well as these nerdy, arbitrary geometry and algebra style questions. So let's get back to sides of triangles, specifically right triangles, and finding the missing sides of the triangle below. So I can see this is a right triangle, and this guy over here, we'll call this side A, we'll call this side B, and we'll call this side C. Now, I know that I could use the Pythagorean theorem here and say that b squared plus c squared will equal my hypotenuse squared. Plugging in the things I know, I'm well on my way, except I've run into a little bit of a roadblock. I don't know what C is, and I don't know what A is. How am I supposed to work with this? I've only got one equation, but I have two things that are unknown. If I have two things that are unknown, then I can't solve this problem, right? If I have two unknowns and two equations, I could work with it. But with only one equation and two unknowns, that's an impossible situation. I can't solve for that. So what do we need to do? Well, we need to work with these angles here. So what we need to do is we need to use trigonometry. You should remember trigonometry to some degree. It's that thing you learned and loved back in geometry and or algebra 2. If you think back, trigonometry is the study of triangle side ratios. And we are calling each of these sides the hypotenuse, the longest side, the opposite, and the adjacent. And what you have to remember, the hypotenuse is always the hypotenuse. It's always the hypotenuse. It's always the one that's opposite of the right angle. However, the adjacent hypotenuse, that might end up changing. And that's all based off of this guy right here, what we call theta. That is our reference angle. And that's always important because you get to choose, for the most part, what the reference angle is going to be. And that's kind of an arbitrary choice. The opposite and adjacent are going to be determined by the reference angle. So you always need to just make sure you make a note of that. Now, what are we supposed to know about the ratios of these sides? Well, that's where this mnemonic device SOHCAHTOA comes in. SOHCAHTOA stands for sine is the opposite over the hypotenuse. I always liked to write it out like this because I know it's a fraction like that. Cosine is the adjacent side of the hypotenuse, and tangent is the opposite over adjacent ratio. Now that in and of itself doesn't seem to make sense, but let's put it into a more mathematical sentence with symbols that we understand. And so we could say that sine of our reference angle will always equal the opposite over the hypotenuse. Cosine of the reference angle is always going to equal the adjacent side over the hypotenuse, and tangent of our reference angle is always going to equal the opposite over the adjacent side. Now, what this should tell you here is that sine, cosine, and tangent are all just operations. They are like mathematical operations that say do this thing to this angle and it will give you this equivalent expression here. So when you see this, you think about it like I'm supposed to be plugging in some calculator thing here and it's going to give me a number. So sine of an angle, really, it's an operation that leads to a number. So when you see this, think that it is a number. Okay, it's going to give me a value. And that's how you want to be able to interpret it because it's going to allow you to do algebraic functions and processes with it. All right. Now, some old mathy people discovered that as long as you have these right angle and other two acute angles, then the ratios of the sides can all be figured out. So now we can solve this arbitrary, nerdy geometry style question. Okay. So we have a right angle here that is, we know it's 90 degrees. Then I have another angle that's 35 degrees. Then I have a third angle, which is unknown. But I know that I can add up these two, 90 and 35, plus my unknown angle here, which is supposed to add up to 180 degrees. And if I do some quick mental math here, I can see that that's going to be, indeed, 55 degrees. Now, when I'm choosing my reference angle, in order to use trigonometry to find my other remaining sides, I get to choose which angle I want to use. So it's pretty arbitrary. But the one thing you don't want to do, you don't want to use your 90-degree one. Don't use that as your reference angle. So I'm going to use this one that was given to me. I'm going to call that my theta. That's going to be my reference angle. Okay? Now, we'll go ahead and call this one side B. We'll go ahead and call this one side C. And we'll go ahead and call this one side A. Now, let's look at this. Instead of A, B, and C, I'm going to instead think about, I know that's my hypotenuse. I know that this one is going to be my opposite side over here. How do I know that this is my opposite side? This is always how I end up starting with it. From my reference angle, I can draw a straight line through my triangle to get to my opposite side. The adjacent side then is the only one that's left. Okay, so now that we've labeled the opposite, adjacent, hypotenuse from our reference angle, now we can start to work with it. Let's go ahead and find that. Let's go ahead and work with trying to find this opposite side. Well, I know my opposite side and I know my adjacent side. So let's go and write down the things that we know. We know my opposite side is unknown, but that's what I want to find. Okay, I know my adjacent side is going to be 12, And then I know my theta, my reference angle, is going to be 35 degrees. Okay? So now what I have to do is I have to see, well, which of my trig ratios is going to utilize opposite and adjacent? And I can see pretty clearly that that's going to be tangent. So we set it up where we say tangent of theta is opposite over adjacent. And we can say then that tangent of 35 degrees is going to equal my opposite side, which is unknown. We'll call that side AB, over my adjacent side, which is 12. So now we just need to do a little bit of algebraic rearranging here. I want to get AB by itself. So since I'm dividing that side by 12, I need to multiply both sides by 12 as well. Now I have 12 times the tangent of 35 degrees. And that's going to give me my sine AB. Now I just need to head over to my trusty calculator here. And that's going to give me this value, 8.40249, so on and so forth. And that's going to give me the length of AB. But we like 3 sig figs, so let's go ahead and call that approximately 8.40. That's rounded to 3 sig figs. So now we have found one of our sides, and that happens to be our opposite side, AB. Next step is to go ahead and try and find our final side. Now, since we now have 2 out of the 3 sides, calling this one 8.40, I could use these 2 sides and plug into the Pythagorean Theorem and I'd be good to go. But I want to utilize trigonometry because I'm in the trig zone. So let's go ahead and now look at, I want the hypotenuse. That's the thing I need to know. I know my adjacent side still. I know my opposite side as well, but since that one I had to round, I would rather use the very precise value and use the original one that's given to me. I'm going to also use the same reference angle just so I don't have to rearrange anything and I don't get myself confused. So utilizing that, I know my adjacent and I know my hypotenuse, and now I need to see, well, which one is that going to be related to? And that's going to be my cosine. And that's going to be opposite over, or the adjacent over the hypotenuse. So cosine of theta is going to equal my A over my H. And I can say then, plugging those things in that I know, cosine of 35 degrees is going to equal my adjacent side 12 over my hypotenuse that I don't know, and my hypotenuse is side BC. So now we're going to go through the same way. I don't like to see the unknown thing in a denominator, so I'm going to multiply both sides by BC. You might think, well, that didn't do anything. I still have work I need to do, and that's true. But that's okay. That's not a big deal. We have now BC times the cosine of 35 degrees, and that's equal to 12. So how are we supposed to get rid of cosine of 35? And a lot of students here will just divide by 35, and they think that's good because that's my number. No, we don't divide by 35 because remember what we said about our trig ratios. The trig ratios are actually actual operations, right? So it's cosine of 35, and that's a number. So we're going to divide the entire thing by cosine of 35 on both sides. Those will cancel each other out, and now I'm left with BC equals 12 divided by the cosine of 35 degrees. We go over to our calculator, and we end up with a value that is something very close to this, 14.649295 ... Again, we'll approximate that and say that BC is going to be approximately 14.6. And that is my final side length. Now we've got all of our angles and all of our triangles, and we have just solved a triangle using trigonometry. Now, the great thing about trig is that someone somewhere did all the really hard work for you. If you look at what we did, we basically did solving a one variable equation using algebra with 1 or 2 steps tops. Super simple stuff. You just have to put the pieces in the right place. So somebody did all that really hard work for you by figuring out all these trig side ratios. You merely need to use those ratios to your advantage. So use a little bit of Isaac Newton there for some inspiration. Get to work on your assignment. Have a wonderful day, and I will see you next time.